is positive, then the function fx is increasing. Remember this? If f prime x is negative, then fx is decreasing. Okay? For both statements, we're talking about on a fixed interval. And this is on some interval from A to B. This was proved using intermediate value theorem. But you can actually see that kind of intuitively it should be clear. Because f prime positive means that the slope of tangent line should be positive. So you really have to have an increasing function because this tangent line is going up. And if the function does that everywhere, then the function really has to be increasing. And likewise, if the derivative is always negative, that means the tangent line always has a negative slope everywhere. And it looks like it really has to be decreasing. As I said, we actually proved that last time using the mean value theorem. I'm not going to repeat the proof here, but I'm just mean value theorem. So this is very useful in sketching graphs. It also tells you to determine local maximum and local minimum. So you can make a statement called first derivative test. Let me state this as a theorem called test. We would like to be able to tell whether something is a local minimum or local maximum. So first of all, we have to assuming f is a nice function, it's a continuous near x0, and then it has derivatives nearby. So fx be continuous at x equals x0 if f prime x is positive before 0, before the point, and negative after. Now what picture do you have? Then fx0 should be what? The local, you can certainly tell it will be increasing and then decreasing. It's continuous at this point. So this is a local maximum. And likewise, if f prime x is negative before and positive after, then it will be a local minimum, right? Right? Is that clear? I mean, you may wonder there are other situations, right? What if it is positive and a positive, right? Or maybe negative and a negative. Then what happens? Let's say if it is positive before and a positive after. Then what happens with the fx0?
It's neither.
It's neither maximum nor minimum. It will be increasing and still increasing up, right? So you can put other situations, but those are really more or less clear. And before and after. Yeah. Neither. It's not a local human. And if it's negative and negative before and after, then it's not either. Still, it's not a local human. Okay. So these will be useful for us to draw a reasonably good picture based on first derivative. Let's look at an example. Here. Let's let f(x) to be x to the 4th minus 18x squared that's 40. So we can use the derivative to determine when f(x) is increasing or decreasing, and also determine local maximum or minimum of f(x), and then sketch its graph. Okay. All right. So we're going to use those criteria to determine those. So I suggest those standard steps. So first, you just compute f prime x. And then determine the critical numbers, meaning f prime x equals 0, or f prime x does not exist. So f prime x equals to 4 x to the 3rd minus 36. Right? Questions on that? Well, let's determine the critical numbers. Critical numbers are the numbers for which f prime equals to 0 or does not exist. In this case, it's simply equals 0 because f prime x does exist everywhere. So set that to be 0, divide both sides by 4, take out a common factor x. So you got x times x squared minus 9 equals 0. Is that okay with us? And this can be factorized into x times x plus 3, x minus 3 equals to 0. Therefore, you got 3 critical numbers. The critical numbers are x equals 0, x equals plus minus 3. Question? And I would suggest you make a table like this. You draw a table, included the critical numbers, In this case, negative 3, 0, and 3. And basically, you want to have the sign of f prime x. A lot of people find it helpful to actually factorize, to look at the factors. It also helps if you actually order them from small to big. Like the numbers here, you start with the smallest. Okay? And then when you order the factors, you also order them according to the roots. In this case, negative 3 is the smallest one, so I put an x plus 3 first. Okay? And then you put x, and that corresponds to 0. 0 is the second one. And then x minus 3. And then you have f prime x. And then you can also question about fx. For each factor, you can put a plus minus signs. Alright? So x plus 3 is 0 here. That's what this will divide this into two parts. Okay? And before negative 3, this will be negative. Right? And after negative 3, this will be positive. Alright, any questions? For x, that is 0. So before that is a negative. After that it is positive. And then for negatives, for x minus 3, this is 0. It's negative before that and positive after that. You may get the impression that you always just change the sign from negative plus at that critical numbers. Not always the case. You understand what I'm talking about? Sometimes you may be in a situation when there's a plus and a plus. How could that happen?
I'm sorry, what?
Sometimes it's not always the case when the sign changes from negative to plus. So you go across that critical number. Like here, you change the sign at negative 3. Here you change the sign at 0. Here you change the sign at 3. What I'm saying that there are situations when the sign just somehow remains to be the same.
Mm-hmm.
Can you explain to me when that could happen?
When the derivative goes up, flattens, and up
Yes,
again.
right. I mean, in terms of graph, that's what you see. And the way to create that kind of phenomenon is that if the function somehow you factorize, it will have not just degree 1, but degree what? Degree 2. Yeah, if it's degree 2, then this will remain to be positive because it's a square. Because it's a square, everybody will be positive. Okay. If it's degree 3, then what happened? It will be negative, not positive, just like degree 1. If it's degree 4, it will be always positive again. So it really depends on the degree whether it is even or odd. But in general, just work carefully and see what the sign is. All right, the rest is fairly easy. F prime f, f prime x. In the product of these times 4, it will be negative here, right?
What did you do?
F prime x. F prime x is this. And this is in fact, if you factorize, is 4 times x plus 3 times x minus 3. Okay? So it's the product of these times 4. 4 does not change the sign. So you multiply 3 negative number, that should be negative. And this here should be positive. Here is negative, here is positive. And that shows that f should be decreasing and increasing, decreasing and increasing. And right away from this table, you can determine, so we already answered this question, when it's increasing or decreasing. It also tells you the local maximum and local minimum from this table. Right. So let me just answer the question again. Fx is increasing on where? Let's see. It will be from -3 to 0. And increasing on 3 to infinity. Right? And fx is decreasing here, which is -infinity to -3 and 0 to 3. So that's where it's increasing or decreasing. And it also tells you the local extremum. So local minimum that is f -3, and you can compute that. I will do that in a moment. And also at here it goes down and up. So f3 is also a local minimum. And f0 should be a local maximum. Local maximum. F0, and you can compute that. Okay, question? All right, let's try to sketch the graph. Before you sketch the graph, I always suggest that you make a table which include the critical numbers, which are -3, 0, and 3, and plus any numbers you like. That's an optional one. All right, x equal to -3, which do you want to plug into? You want to plug into fx. Not this one, not the f prime. Some people make that kind of mistake. Yeah, so you have to plug into this one. Right? So what do you get? -3 to the 4th, that's 81, right? So it's really 9 times 9. And then 18 times 9 plus 40. And that is a negative, you can take out a common factor. So this part is -81, right? There's 2. It's -81. If you take out a 9 out, and then what's left is -9. So -81 plus 40, and that is -41. So this is -41. 0 gives you +40. And 3 gives you a -41 as well. You have the same value. Okay, let's see if we can sketch the graph. So I suggest that you plot the points first. Because these numbers are okay. 1, 2, 3, those are not too big numbers. You can use the usual scale. So this is 1, this is 2, this is 3. So those numbers are fairly big. Let's try to use a different scale. Otherwise the graph looks very strange. It's harder to do. Let's say this is 10, 20, 30, and 40. So this is my 1, 2, and 3. All right. -3, -41. So 3, 10, 40. So that's roughly here. 0, 40 here. 3, -41 here. All right, so we got those 3 points. How are we going to connect them? The graph is more or less here. I mean, if you look at those things here, it goes down and up and down and up. You know, they are almost there. The graph is almost there. Okay. You have some idea what the graph may look like. And then to have an accurate one, you plot the points here, right here, and then you just use this pattern. So it goes down, up, down, and up. That's the graph. In this particular graph, notice that it only has even powers. This implies that if you change the sign of x, replace x by negative x, it remains to be the same. So notice that if you replace x by minus x, that remains to be fx, right? And those functions satisfying that property has a particular name. What's called? Yeah, that's called an even function. And if it's an even function, it should be symmetric with respect to what? Not quite. No. The y-axis. Just keep on trying. So, I mean, basically it means that whenever you have negative xy, then whenever negative x comma y is on the graph, x comma y is also on the graph. That implies it's symmetric to the y-axis. Okay. So this picture basically shows the idea how first derivative can be used to understand the graph. Let's keep on going and study the impact of second derivatives. Let's try to understand the following. How about second derivative? So we would like to understand if the second derivative is positive, then what happens? To understand that. And if second derivative is negative, then what happens? Okay? So that's the kind of question we would like to answer here. Well, second, I want some more rooms here, so I'll just erase this. Second derivative is positive. Implies what?
Is that a minimum?
This is the question that I would like to answer. Okay.
Yes.
Well, remember, second derivative is the derivative of the first derivative. Yeah.
The first derivative is changing at an increasing rate?
First derivative is changing at an increasing rate. Yeah, it's increasing. Let's just simplify the English. I'm trying to understand what exactly. So yeah, that's right. So it implies first derivative as a function is increasing, right? We basically apply what I just erased. So it implies first derivative is increasing. Is that clear to us? And that's because second derivative is the derivative of the first derivative, right? So f prime as a function has a positive derivative, therefore it is increasing, right? And now let's try to understand what does it mean to have a first derivative to f prime be increasing. What does that mean? That means the slope of tangent line is increasing. Okay. So if you try to understand the graph of some function, I mean, all the way. I mean, I can try to draw some kind of graph here, and you can sort of see where it would satisfy this, where it would not satisfy that. So here, the first derivative is kind of positive, right? Right? And here, it is still positive, right? But can you see, relative to the first one, which one has a bigger first derivative? I mean, yeah, first derivative, that's right. Which one has a bigger slope out of these two? This one is steeper, so it has a bigger slope. The slope is getting smaller, right? And here it is still increasing, but even smaller. Here it becomes 0, right? And then after that becomes negative. So clearly it is kind of decreasing. You kind of, if you drive on the speed, you're kind of turning to the right, I think. That's the feeling. You're kind of turning your wheel to the right. Right? If you drive on the curved speed, driving to the right, the wheel is turning to the right. But after that, you kind of see that, okay, so here you have a negative slope, and here the slope becomes less negative, and then 0, and then becomes positive. So I hope you kind of see that from here to here, from here to here, f prime is decreasing. Is that clear to you? And after that, f prime is increasing. If you can see that. So, because f prime is increasing, we must have a picture like this, rather than a picture like this. So I'm going to just kind of draw a picture of the graph. It has to look like this. You can think about it as like a smiling face rather than an angry face. So, and people use the term concave up to describe that. All right, so fx is concave up. That's the word. Concave up. And the graph looks like this. All right? And once again, if f double prime is a negative, just like before, that will imply f prime x is a decreasing function. And then out of the pictures I draw out of the two pieces, it will be the first piece. Right? And here is when f prime is decreasing. Therefore, you have a picture like that, and we say fx is concave down. And we draw the picture here. A little bit of crowd over here. So the graph should look like something like this. Okay? And there will be a second derivative test following this. I feel like I should move on and do the graph, and then later talk about a second derivative test. So leave some space here if you want. And we'll talk about that later. Second derivative test. Do that in a moment. So this means we can draw better pictures. We can, yeah, we're going to do it just for this one. So that means that in general, we know a graph can be increasing or decreasing. But how does it increase? It means that we can have a graph that is increasing, but you can have increasing like this, or increasing like that.